about some precipitation notes. So let's do a little quick review on what KSP would be. So I have an equation here, which is mx, and it's a solid, so I'm assuming that's a salt. And it dissociates into m plus and x minus. So we know with equilibrium constants that we can only have gases and aqueous solutions in our equilibrium expression. So KSP, which means solubility product, would simply be KSP equals my products over my reactants. And in this case, because I do not have any reactants that are aqueous or solids, or aqueous or gases, that would be all that I would write for that. If there would be some coefficient right here, then that would also go right there. So that would have to look something like that if you needed to adjust it. But you've already gone through that. So that's what that would be. So what is a precipitation? So precipitation, as you know, is when a solid forms when two aqueous solutions are mixed together and there's an insoluble product that is produced. The problem is that all items in theory are somewhat soluble. Just most things that are insoluble only dissolve a very little amount. So we want to talk about what that means. So what we're going to do is we're going to predict whether precipitation occurs or if a dissolution occurs. So what we're really doing is we are predicting whether a precipitation or a dissolution occurs. So what is going to occur in my products? And whenever you're predicting, what have we learned? When we're saying predicting and we're talking about equilibrium, we're talking about Q, okay? Our reaction quotient. So we have two options here. Q is greater than KSP, or Q is less than KSP, okay? So we talk about Q versus KSP and kind of thinking that if my K is my equilibrium, wherever that is on my equation, is if Q is greater than that, it needs to re-meet up with my K, right? So if my Q is greater than my K, regardless of where my K is, my Q has to come back to my K. So that means I'm too far this way. So I have too many products. Okay? So if I have too many products, it needs to drive back this way. And what am I going to make? I'm going to create more solid. So precipitation occurs. If my Q is smaller than my K, so here's my K, wherever that may be, and my Q is this way, it means that I am actually going to be driving it more towards the products. So if I'm going to drive it towards the products, I'm going to create more of that, which means I'm creating more ions, right? So that means initially I had too many reactants. And I guess what we can just think of it this as is that either that's dissolution or you can say that there's no precipitate. Okay, so that's kind of what we're going to do today. We're going to utilize KSP and we're going to be predicting whether or not things are going to precipitate or not, or how much is going to precipitate or how much is going to dissolve. So we're going to do that with 3 problems today, and they're varying degrees of difficulty and approaches, okay? So, our first problem. We have a solution is made of mixing 750 milliliters of 4 times 10 to the negative third CnO3 and 300 milliliters of 2 times 10 to the negative second molar of KiO3. Okay, so what we need to do is we need to talk about whether or not the CiO3 will precipitate out. That's the question. Will it precipitate out? And I know what you're thinking, well, where did that come from? Well, first off, it's always important to have an equation. So if I take these two, just so you can physically see this, and you would draw an equation to this, hopefully you would recognize, hey, this is a double replacement reaction. And that's what I would get. We clearly know, first off, if you say these are solutions, I have a Q. Based on our solubility rules, potassium nitrate are extremely soluble. And this is going to be the question. Is that a solid? And how much of it? So that's the one I want to focus on. So what we need to do is take that and now plug it in to our solubility product or our salt dissolution balanced equation. So what I really do is I focus on this right here. Is how much of this is going to actually occur? How much of that is actually going to occur? So if we are wondering, will it precipitate out? Will something happen? Predict. If it ever says anything like that, just the very fact that it says that, you need to think Q. Let's find out where they're at, and we're going to compare it to our K. So we're going to take the amounts that we have, and we're going to plug it into our equilibrium expression. So right now, I'm going to write this kind of small under here, but my equilibrium expression would be KSP equals my two products. So let's plug these in. But instead of saying KSP, which in theory I will transplant that, and I would say right now 1.9 times 10 to the negative 10th, because that's been given. We're going to take that out, and we're going to say Q instead. So I'm going to use this exact same equation. So now, you got to understand, this is concentration. And if this is concentration, it's moles over volume, right? So that's really important that you're understanding that. So I have to actually get it back into moles. Right now I have molarity. And that is a typo. That should be an M right there. And I have volume, and I'm mixing these together. Okay, so what is the new concentrations of each? So what I'm going to have to do is I'm going to take my volume. So I'm going to do it of the CE. So this results in my CE, and this is of the IO3. So I'm going to take my volume, and you could do this by liters. My gosh, you could totally do this by liters, but I'm going to do it in milliliters and then just redivide it by milliliters. So I have 750 times the concentration, which is moles over liters, over the total volume. So I have 750 plus 300 milliliters. Okay? So I've converted it to moles, in this case millimoles, but then I'm redividing it over milliliters, so that cancels it all out. Otherwise, you could do it by 0.75, which is liters, and then put it over the total volume, which would be 1.05 liters instead of 1,500 liters, or 50 liters. All right, so that's of the CE. Let's do the IO3 minus. So same concepts. You're going to take the volume. So I'm going to take 300 milliliters, multiplied it by the volume, or the molarity. And I'm going to put it over the total volume. Okay, so when I get that, I'll move this. I get a value. And Q, if I calculate this out, I get 5.32, I'm going to highlight that just so we can see it, times 10 to the negative 10th. Well, what does that mean? I have to compare it to my k. And my k is 1.9 times 10 to the negative 10th. So what that means is it's slightly greater. So then what does it mean? Can I answer this? Will this precipitate out? Well, I am saying that there's this much, if this is the maximum amount that can dissolve, the maximum amount that can dissolve equals my KSP, I'm saying I have more than that. I am saying that I have more than the maximum amount that can dissolve. So if this is my K, my Q is over here, it's got to come back. It's got to come back, so it will precipitate. Precipitation will form. So yes to precipitation. And that answers that question. Okay, so when you ever ask if it's going to precipitate or not, if you're ever asking to predict in any equilibrium problem, you are always going to solve for Q. Okay, let's go to the next kind of problem. We're going to just quickly get this down way lower. All right, so a solution is created by mixing 150 milliliters of a magnesium nitrate solution and 250 milliliters of a sodium fluoride solution. And I know, be mindful, sometimes numbers are given to you in an odd way. I think it's just for sig fig purposes. So we can obviously move these over just so you know. Let's hold on to those zeros. So that could be that, right? So why don't we use those numbers instead? It'll just make it easier. Here it is. Find the concentration of Mg2 plus and F minus at equilibrium. So please be mindful. If you're given ions, these are both AQ. Right? So I'm wanting to know how much of my ions have dissolved. Has all of this dissolved? Is some of it only going to dissolve? If only some of it dissolves, that means the rest of it actually precipitated out. So here's my equation, right? Or my final product. And if you're ever given of a KSP, that's the compound in question. So literally, what I'm wondering is this. Here's my solid. That is my solubility balance equation that I need. Okay, so what we need to do, again, is first off, we need to find out where this is going. Okay, so if I look at this problem right now, I'm just going to write down what I know. So if I write down what I know right now is I have a certain number of millimoles, okay? Like beforehand, if I just talk about the compounds that I'm given. So if I have 150 milliliters times 0.01 molarity, then what I have is 1.5 millimoles. And if I look at the other one, same idea. Let's be consistent. I have 25 millimoles. And then this is a solid, so this isn't going to go that way. So the question is this added or is this subtracted when I look at it in my icebox? So what we need to do is understand, is it going to the left or is it going to the right in the first place? So we need Q. Whenever we don't know, we need Q. So what we're going to do is I'm going to plug that in like I did before, and we're going to see where that leads us. So let me just write that over here. So let me write down what I have first. So I have Mg and I have F minus. Because I have a coefficient, I need to put that as a squared sign right there, right? So now, unfortunately, these are just millimoles. I need to put them over total volumes. But I've already figured out the moles. So what I can do is I have 1.5 millimoles of my Mg over the total amount. So 150 and 250 milliliters, that will be 400 milliliters total. So the millis cancel, and now I have moles over liters. So that's that amount, and then I have, where did I have? 25 millimoles over 400 milliliters squared. Make sure that you square that. So if I get all that, my Q, I've done some of the math for us already, is 1.46 times 10 to the negative fifth. What does that mean? Well, it's predicting that if this is the maximum amount that can dissolve, that this is like saying it's my K, but it's my Q, that is much greater than my KSP, much greater. So it's going to drive it to the left. So what we're going to do, we're going to completely drive it all the way to the left. We don't know how far it's going to drive to the left, so let's just drive this as far as we can. So how far can we go? It's kind of like acids and bases. Let's consume one of them. So if I'm driving it this way, then this is going to be minus x, and this is going to be minus 2x. Okay? So if I'm going to drive it all the way, I need to consume it to 0. So that tells me something. It tells me that x is 1.5. So if x is 1.5, then 2 times x is 3, right? So I'm going to have 22 millimoles left. So I've driven it to left. Here's the problem. You're forcing it. We're going to drive it to left. This, I believe, is the hardest problem of these 3 problems. Now it's going to redissociate. You got to have something, okay? You got to have something. The reaction needs to still reach an equilibrium. Okay? So if I plug these numbers in right now into this expression, it's not going to get that KSP. I need to have values that equal that KSP. So now what I'm going to do is I just redissociate it one last time. It's kind of like an equivalence point in a titration curve. So I'm just going to actually utilize this right here. So I'm just going to kind of just go right there. Okay, we're going to drive it back. So now I have a starting point, because I've already written here, so of 22 and 0. Okay, so now I'm saying I'm adding them again. So it's going to be plus x. This will make sense more in a second. Plus 2x. So I have x, 22 millimoles plus 2x. And we have one problem. And the problem is that, and I should have done this beforehand, when we do these, it needs to be in concentration. It needs to be in concentration. So what I should have done, we're going to do it right now, I'm going to fix it, is that I should have taken this and I should have put it over a total volume. Right, so we have 400 milliliters right there, so that becomes a different number. So let's actually fix that, because that we're going to need anyway. You cannot have that in any other way. So if I do that, I did not calculate that right. I get 0.055 molar, okay? So now I have 0.055 plus 2x. All right, so if you're looking at that, you probably now recognize that that looks a lot like a lot of other equilibrium expressions that we've done in the past. So what we need to do now is we need to make sure that we now plug that in to an equilibrium expression. So now I'll just do it on the side here. I'm going to be utilizing my KSP, which I can't see any longer. Let's look at it. My KSP is 6.4 times 10 to the negative 9th. So 6.4 times 10 to the negative 9th equals x times 0.055 plus 2x squared. I am plugging it into this. All right, just my KSP instead. This is now my equilibrium expression. So I cross that off, and I get, I'm going to solve for x. And x is 2.15 times 10 to the 6, negative 6. So now the question was, what is my Mg2 plus and my F minus. So my Mg2 plus is X. So concentration of Mg2 plus equals that. And my concentration of my F minus is going to equal 0.055 plus 2x, which basically equals the same amount. So those are the concentrations of my ions at equilibrium. Not all of it dissolved, but the maximum amount that did dissolve are those two values, and they equal my KSP. Okay, I think that's the hardest question, because what you have to do is actually drive the reaction back and then flood it forward, reaching equilibrium. Let's take a look at our last problem. Again, they're all very, very different. So it says you have a solution, and it's actually a solution of KUI and PBI2, but of that, the CU, and well, here, I can get ahead of myself. You have that amount, that molarity of each of those metals, okay? And if they were all sitting in there, if I gradually added I minus, so I slowly add I minus. So CUI and PBI2 are both not very soluble. So they're gonna precipitate pretty quickly. And how do we get an I minus? Well, we could be adding NaI, Ki, something else that's soluble, so that alkali metal is going to break off, and then I have that I. So it's basically a double replacement reaction, and you're going to be making a precipitate. The question is, which one's going to precipitate first? So if you do that twice, which one are you going to actually precipitate? Okay. So what you can do is you got to think about it in terms of this. And you don't have to think of it this way necessarily, but it's which ones of these is going to happen first. So you have this, and you have, so this is actually just good practice if it ever asks what are the reactions or the balance equations for these. You have to understand these always, all right? And then what I did was I gave you, I'm giving you right now the KSPs for both of those. So we can write those on the side. We definitely can, and you know, I can do that. So KSP of the CU is 5.3 times 10 to the negative 12, and the KSP for the lead iodide, lead 2 iodide would be that. Okay. So what do we have to do? Well, what we do is we simply plug them in to a KSP expression. So again, the most confusing thing for students is, what does the KSP equation actually give me? Well, in this case, this KSP would be this equation. So if you were asked for KSP expressions, that's what that looks like. And then this one, I line this up. So what we are going to do is we're going to place the amounts in there and then figure out how much I we're going to need, okay? And whichever one is the least amount would happen first. So if I dump in, I'm making this up, 0.1 molar of I minus, and that made a precipitate, and then I added 10 molar of the other into the other solution with I minus, and then that finally precipitated. Well, the 0.1 is going to precipitate a lot sooner than the 10. So we're going to let the KSP kind of tell us what to do here. So let's pick one at a time here. We'll do the CU first. So I take my equation, and I was told I have 1.0 times 10 to the negative 4th molar of my Cu. So then my X, or my I minus, is all that's left, okay? So all we got to do is calculate that. So basically, you imagine that to be X. So my I minus for that to equal 5.3 times 10 to the negative 12th would be 5.3 times 10 to the negative 8th molars. So that's of my I minus concentration. Okay? For that one. So that's if I would just solve like act like that's X. If I do PB, right, PB I have 1.4 times 10 to the negative 8th equals, let's find out what I was given. I said that I have 2 times 10 to the negative 3rd molar of that. Of my PB, I want to make sure I got that number right. And it's 2.0, but it'll still work. And then I'm going to say of my I minus, but I have to square that, so it's like it's X squared, okay? So when I solve for the I minus for that, so let's recap. It takes this concentration, once I reach that amount, so I'm just sprinkling it in basically, at this amount, this is the maximum amount that can hold. Any more, it's going to precipitate, okay? If I add that amount, that's the maximum amount of iodine that I can add before the PB starts to precipitate. So which one would precipitate first? It'd be the lowest amount, right? It takes the lower concentration. It would take a lower concentration to precipitate out the copper. So honestly, it would be of the copper iodine. So solubility and solubility products help us to determine how much can dissolve. And if I overload that, I go past my KSP, then I am now creating a precipitate or a solid.